Hello everyone. Welcome to the sixth lecture on partial differentiation. In this lecture, we'll discuss about Jacobians. Let u and v be functions of two variables x and y. Then the Jacobian of u v with respect to xy is the determinant del u divided by del x, del u by del y, del v by del x, and del v by del y. Whereas this del u by del x is partial derivative of u with respect to x. Del u by del y is partial derivative of u with respect to y. Similarly, del v by del x is partial derivative of v with respect to x, and del v by del y is partial derivative of v with respect to y. So if u and v are two functions of two variables x and y, that means u is a function of x and y and v is also a function of x and y, then the Jacobian of u v with respect to xy is the determinant. And this Jacobian is represented by symbol j ub divided by xy or del uv divided by del xy. These symbols are used for the Jacobian of uv with respect to x and y. Here we have an example. If x is equal to r cos theta and y is equal to r sin theta, then the question is find out Jacobian of xy with respect to r theta. Here we can see that x is a function of r and theta and y is also a function of r and theta. Now the question is to find out the Jacobian of these two functions x and y with respect to two variables r and theta. Now since x is equal to r cos theta, we can find out the partial derivative of x with respect to r and with respect to theta. So partial derivative of x with respect to r is cos theta, because we are differentiating x with respect to r partially. So theta is treated as a constant. So here in x is equal to r cos theta is a constant. So we are differentiating x with respect to r. So our partial derivative of x with respect to r is cos theta is taken as it is because it is a constant, and the derivative of r with respect to r is 1. So del x divided by del r is equal to cos theta. Similarly, partial derivative of x with respect to theta, here r is treated as a constant. So our r is constant and the derivative of cos theta is minus sin theta. R we have taken as it is and derivative of cos theta with respect to theta is minus sin theta. So partial derivative of x with respect to theta is minus r sin theta. Similarly, our y is r sin theta. Now we have to find out del y by del r and del y by del theta. So the partial derivative of y with respect to r, here theta is treated as a constant, so we have taken sin theta as it is, and the derivative of r with respect to r is 1. So del y by del r is sin theta. Similarly, partial derivative of y with respect to theta is, here r is a constant, it is taken as it is, and the derivative of sin theta is cos theta. So del y by del theta is r cos theta. Therefore, the Jacobian of xy with respect to r theta is the determinant of these four partial derivatives. Now we have seen that del x by del r is cos theta, del x by del theta is minus r sin theta, del y by del r is sin theta, and del y by del theta is r cos theta. Now putting these values inside this matrix, we have this. Now the determinant of this is r cos square theta plus r sin square theta. By taking r common, we have r into cos square theta plus sin square theta, which is 1. So the Jacobian of xy with respect to r theta is r. Now here are some of the properties of Jacobians. The first property is, if u and v are functions of x and y, then the Jacobian of uv with respect to xy into the Jacobian of xy with respect to uv is always 1. This is the first property of Jacobian. If u and v are functions of x and y, then Jacobian of the function uv with respect to xy into Jacobian of xy with respect to ub is always 1. Now the second property of Jacobian is if u and v are functions of r and s, whereas this r and s are further functions of two variables x and y, then the Jacobian of uv with respect to xy is Jacobian of uv with respect to r and s into Jacobian of rs with respect to xy. Here we have seen that u, v are two functions of two variables. U is a function of r and s. Similarly, v is a function of r and s. Further, these two variables r and s are functions of other two variables x and y. So the Jacobian of u, v with respect to these two variables x and y is nothing but product of these two Jacobians. Jacobian of u, v with respect to rs into Jacobian of Rs with respect to xy. This property is known as chain rule of Jacobian. Now the third property of Jacobian is let u, v be two functions of two independent variables xy. These xy are independent variables. If u and v are not independent, then the Jacobian of u, v with respect to xy is 0. Here these x, y's are independent variables and this u and v are functions of these two variables. If these two functions u and v are not independent, then the Jacobian of u, v with respect to xy is 0. That is, if u, v are not independent, then the Jacobian of u, v with respect to xy is equal to 0. Now let us prove these three properties of Jacobian one by one. The first property is if u and v are functions of x and y, then the Jacobian of u, v with respect to xy into the Jacobian of xy with respect to u, v is 1. Now the proof is let u, v be functions of x and y. That means u is a function of xy, u is equal to f of xy. And v is also a function of xy. That means v is equal to g of xy. We know that Jacobian of u, v with respect to xy is the determinant of the partial derivatives of u with respect to x and y and partial derivative of v with respect to x and y. Similarly, the Jacobian of xy with respect to uv is del xy divided by del uv. That means del x by del u, del x by del v, del y by del u, del y by del v. Here we have these two Jacobians. Here we have the Jacobian of u, v with respect to x and y. And here we have Jacobian of xy with respect to u and v. Now the product of these two Jacobians, Jacobian of u, v with respect to xy into Jacobian of xy with respect to u, v is this, the product of these two determinants. Since u, v are functions of xy, differentiating u, v with respect to u, v itself, we have del u by del u is 1, del u by del v is 0, del v by del v is 1, del v by del u is 0. Now let us find out this del u by del u, del u by del v, del v by del v and del v by del u. We know that del u by del u is nothing but del u by del x into del x by del u plus del u by del y into del u by del u. But here we have seen that del u by del u is 1. So this term, this sum is equal to 1. Similarly, what is del u by del v? Our del u by del v is del u by del x into del x by del v plus del u by del y into del y by del v. And here we have seen that del u by del v is equal to 0. So this expression is 0. The third one is partial derivative of v with respect to u. That means del v by del u. This is equal to del v by del x into del x by del u plus del v by del y into del y by del u. And here del v by del u is 0. So we have this is equal to 0. Now we have to find out del v by del v. Now del v by del v is equal to del v by del x into del x by del v plus del v by del y into del y by del v. And we have seen here that del v by del v is equal to 1. So this is equal to 1. Now if we replace this in this product of these two Jacobians, we have here we have the product of two Jacobians. The Jacobian of ub with respect to xy and Jacobian of xy with respect to ub. Their product is this. And we have seen that del u by del x into del x by del u plus del u by del y into del y by del u is 1. So we can replace this 1, 0, 0, 1 in this determinant. So we have 1, 0, 0, 1. And now finding out the determinant is 1. So the product of these two Jacobians is always 1. This is the proof of the first property of Jacobian. Now here we have an example based on the first property of Jacobian. If x is equal to uv and y is equal to u plus v divided by u minus b, then find out what is the Jacobian of uv with respect to xy. Here we will use the first property of Jacobian, because here it is given that these x and y are functions of u and v, and we have to find out the Jacobian of uv with respect to xy. Here xy are functions of uv, and we have to find out the Jacobian of uv with respect to xy. It is observed that it is easy to find out the Jacobian of xy with respect to uv, because it is given here x in terms of uv and y in terms of uv. So it is easy to find out this Jacobian. But we have to find out the Jacobian of uv with respect to xy. Now Jacobian of xy with respect to uv is this determinant. Del x by del u, del x by del v, del y by del u, del y by del v. Here our x is equal to uv. So this is the partial derivative of x with respect to u. So we have just replaced x by uv because our x is uv. So the partial derivative of uv with respect to u, here v will be treated as a constant. Similarly, del x by del v, we have replaced x by uv. So partial derivative of uv with respect to v. Similarly, here we replaced y as u plus v divided by u minus b, because it is given in the example that y is equal to u plus b divided by u minus b. So we have to find out partial derivative of u plus v divided by u minus v with respect to u. Similarly, here we have del y by del v. That means partial derivative of y. Y is over u plus v divided by u minus v with respect to v. Now taking the partial derivative of these four terms, we have this, because partial derivative of uv with respect to u is v. As v is a constant here, v we have taken as it is, and the derivative of u with respect to u is 1. Similarly, partial derivative of uv with respect to v, here u is a constant, u is taken as it is, and the derivative of v with respect to v is 1. So we have the partial derivative as u. Similarly, partial derivative of u plus v divided by u minus v is minus 2v divided by u minus v square, because the partial derivative of u plus v divided by u minus v with respect to u, here b is treated as a constant. Now we have to take u minus b, partial derivative of u plus b, minus u plus v into partial derivative of u minus b with respect to u, divided by u minus v whole square. Now this term, partial derivative of u plus b with respect to u, is 1 because here b is a constant and the derivative of this b is 0, and the derivative of u with respect to u is 1. So we have in the first term u minus b into 1. Similarly, in the second term, we have the partial derivative of u minus b with respect to u. Here b is a constant, so it becomes 0. Now the partial derivative of u with respect to u is 1. So the second term becomes minus u plus v into 1 divided by u minus v whole square. That is equal to minus 2b divided by u minus v whole square. So now we have with us del by del u of u plus v divided by u minus b as minus 2b divided by u minus v whole square. So here we have this minus 2b divided by u minus v whole square. Similarly, the partial derivative of u plus v divided by u minus v with respect to v can be obtained in this process, which is equal to 2u divided by u minus v whole square. So here we have 2u divided by u minus v whole square. Now finding out the determinant of this, we have 2uv. We have to take the product of these two. 2uv divided by u minus v square. Here we have 2uv divided by u minus v whole square plus, because here we have a minus sign, product of these two, which is 2uv divided by u minus v whole square. So we have the second term 2uv divided by u minus v whole square, which is equal to 4uv divided by u minus v square. Now the Jacobian of xy with respect to uv is 4uv divided by u minus v whole square. From the first property of Jacobian, we know that Jacobian of uv with respect to xy into Jacobian of xy with respect to uv is 1. Now we have this with us, Jacobian of xy with respect to uv. But our question is to find out Jacobian of uv with respect to xy. So we can use the first property of Jacobian here to find out the Jacobian of uv with respect to xy. Now by putting the value of Jacobian of xy with respect to uv here, we have this Jacobian of uv with respect to xy into 4uv divided by u minus v square is equal to 1, because this 4uv divided by u minus v whole square is our Jacobian of xy with respect to uv. Here it is. So Jacobian of uv with respect to xy is equal to 1 divided by this, which is equal to u minus v whole square divided by 4uv. So in this example, we observed that if there is a question that x and y are functions of two variables u and v, and we have to find out Jacobian of uv with respect to x and y, then the first property of Jacobian can be utilized. So this is about the first property of Jacobian, and we have seen one example based on the first property. In the next lecture, we'll discuss about second and third property of Jacobians, and we'll work out some example based on second and third property.